Okay, we have an island. Thousand immortal. Non-reproducing people. Okay? 500 of them are sane, 500 demented. If you're demented, you're not sane. If you're sane, you're not demented. Okay? So these are mutually exclusive categories. Every month, %20 of the demented become sane. % of the sane become demented. So, in this case, 20% of these will become these. That's 100 of them, right? So you're going to have 100 demented people that become sane, and you're going to have 10% of the sane, 50 sane people become demented. So then you're going to have 550 sane and 450 demented. Okay? Then 10% of these will become these, and 20% of these will become these. That's going to be 90 go this way, 45 go this way. You're going to end up with 595 sane and 415 demented. It's going to continue. But the numbers are going to change more and more slowly because you're approaching a point where 10% of the sane is equal to 20% of the demented, which will happen when you have twice as many of these as you have these. Well, if you got twice as many of these as you have these, and they add up to 1,000 because they're immortal, non-reproducing, it's got to be. It means you're going to have 666 and 2/3 sane, 333 and 1/3 demented. And all that's pretty easy to reconcile and understand. So we know that the sane demented vector starts out at 500, 500, okay? And then it approaches this. The total number is constant, which means the number sane plus the number demented is 1,000, means you have a linear relationship. Anytime you have an extra sane, you're going to have one less demented. So if this is a number of sane and this is a number of demented, your vectors, all possible population vectors, are here. The limiting vector, the vector that they always approach, is this one. So wherever we start here. Then we're going to move a little bit less, but still getting closer, a little bit less, and in smaller and smaller jumps, we're going to approach this population as a limit, but we're never going to get there. It's going to be an asymptote. Okay? So explain that in terms of eigenvectors. Well, it's going to turn out that this is an eigenvector for the transformation, and you've got another eigenvector that's parallel to this. So these things always move along the eigenvectors, and if you do this in an eigenvector basis, you can totally understand it. So let's do that. Okay, the matrix that takes 10% of your sane to the demented and 20% of the demented to the sane is very simple. 2 by 2 matrix. We'll use S prime and D prime for the numbers after transition, okay? And the matrix is very simple. If 10% of your sane stay sane, become demented, that means the other 90% stay sane. So if you multiply 500 by 90%, you get 450, right? Well, that means whatever you do, 90% of your sane are going to stay sane, so you multiply the number sane by 0.9, and that contributes to the number sane after the transition. And then 20% of your demented becomes sane, so you're going to have to multiply the number demented by 20%, which is 0.2. And now you have S prime is going to be 90% of your sane plus 20% of your demented. Okay? Simple enough. And then for the other one, okay, what do you do to get the demented? Well, 10% of you get 10% of your sane. So you're going to have a 0.1 here, and 20% of your demented becomes sane. That leaves 80% that stay here. So there's your matrix. Okay? Make sense? Mm-hmm. So after and transitions, because every transition you're going to multiply the new number by this matrix. You're just going to keep multiplying by this matrix, so you might as well just multiply by the nth power of the matrix. So go ahead and calculate the nth power of this matrix. Can you do it? Not until you diagonalize it, you can't. So find its eigenvalues.